All right, still looking at three-phase power calculations. We're going to look at loads or supplies. We're going to look at both of them, a supply. If we reconnect the supply from Y to delta and do a little review with it and see what its effects are on the power, maximum power output. We are also going to do that with a load as well. We're going to take a load of three equal oppositions, connect them in Y to a supply, and then disconnect them, reconnect them in delta to that same supply, and note the differences again, a little bit of review, and then see what happens with power. So let's start off with here with a supply. So in this supply, there's could be the secondary of a transformer, or it could be an alternator. So each one of the coils is rated at 120 volts and 20 amps. So first let's look at if it's connected up in Y. Well, in Y, the phase voltage is going to be equal to 120 volts because that's what's being produced. So that's V phase. And we know that the line voltage is going to be V phase times root 3. So that's how we get 208 volts. The phase current, well, that's the actual rating through each coil. It's 20 amps. And the line current, well, in Y, I line is the same as I phase. Okay, let's have a look at the delta side here. Well, the same ratings apply here. This coil will get 120 volts produced across it, and 20 amps is its maximum. Well, over on delta, V line is the same as V phase. So the line voltage is also 120. We know that line current on the delta is equal to I phase times root 3. So 20 times root 3, about 34.6 amps. And so this is a bit of a review. We've done this already. And a little summary chart. So notice that the line current ends up root 3 higher. The V line is root 3 less when it goes to delta. The phase voltage and I phase are the same. Well, what happens with apparent power? So if you recall, we take the phase voltage to figure out the S of the phase voltage times I of the phase. So that's going to work out to 120 volts times 20 amps. All right. So we are looking at about 2400 VA. And the apparent power total, well, we can take the S of the phase and times it by 3, or we could use our power formula, S total equals V line times I line times root 3. Either way, it's going to work out to be approximately 7200 VA. Well, going ahead, let's look at the delta. Apparent power of the phase, well, that's V phase times I phase. So 120 times 20, that's still going to be 2400 VA. Apparent power total, well, we can use the same thing. S to the phase times 3, or V line times I line times root 3, get us the same thing. And that's still going to work out to be approximately 7200 VA. So a little summary chart. Basically, the apparent power produced in each phase is the same. And the total apparent power that this thing can put out is the same, whether this generator was Y connected or delta connected. Same output VA capability. So the difference is the line voltage in delta is root 3 smaller, but the line current is root 3 higher. So that's what gives you why it has the same output VA. So we have much different results if we're looking at a load. So in this time, we're going to take three equal resistors, and they are three 12-ohm resistors. And in the first scenario, we are going to connect them up to a 208 supply and in Y. So we know V phase is V line divided by root 3. So our phase voltage is 120. Our line voltage is 208. Our I of our phase is the V phase divided by the impedance in the phase. Well, in that case, so it's 120 divided by 12. It's 10 amps. Line current, same as phase current in Y, 10 amps. Let's compare that to delta. Well, over here on the delta, we have 208 volt line. V phase is the same as V line. So you got 208 volt drop across each one of these. So V phase is 208, V line is 208. So our phase current would be our V phase, 208, divided by our 12 ohms. Remember, these are all 12 ohms reconnected. That'll come to about 17.33 amps. If I multiply that by root 3 for my line current, because I line is equal to I phase times root 3, we're going to come out to about 30 amps. So a little review. And if we look at a comparison chart, we see that the line voltage is root 3 higher. Phase voltage is root 3 higher in delta. Line voltage is the same. Phase current, because the phase voltage is root 3 higher, ends up being root 3 higher. And the line current, well, that's another root 3 higher yet on in the delta from phase to line. So it comes out to 30 amps. We have a difference of 3 times greater current. Well, let's have a look now at apparent power. What's the apparent power output of these? In this case, it is all true power because it's resistors. So S of the phase is V phase times I phase. So 120 times 10, that's 1200 VA. S total, well, we could take S of the phase times 3, or V line times I line times root 3. It's going to work out to 3600 VA. Okay. So why don't we have a look now at these three loads connected up in delta. What's the apparent power load of that? So V phase times I phase. This is my phase apparent power. So that'd be 208 times 17.33. So we're looking at approximately 3600 VA in the phase. Total three-phase output would be S of the phase times 3, or V line times I line times root 3. It'll give you the same answer. And we're looking about 10,800 VA. Well, a little summary chart. We'll see that comparing the two, that we've got 3 times more apparent power in the phase, and that makes 3 times more apparent power total in the end. So when I reconnect a load from Y to delta, we have 3 times more apparent power. So make sure you commit that to memory, because you're going to be asked to quickly go back and forth between a Y connected load and a delta connected load, and you're going to have to know that a delta connected load will use 3 times more power than it would if it was connected in Y. So hopefully this helps you out, and we'll see you on the next video.